Now some of you probably just saw that, that's good. You wouldn't have to do all this. You're doing it in your head, but the radius is 2. So I'm going to go from 0 to 2. Radius of that circle is 2 because you got x squared plus y squared equals 4. So I'll just say radius equals 2. If you want to make this picture really good, just put 2 tick marks here. I don't know if it looks so pretty, everyone. I'll try to make some really like 1, 2, 1, 2. And you can label this. This intersects at y equals 2. And that's x equal to 2. Because this is the x-axis, this is the y-axis, and that's the z-axis. Right? Cool. Now, if I'm going polar, what letter's automatic? R. You already theta. What's this become though? Is it 4? Is x r cosine theta or just cosine theta? It's r cosine theta. So this is what I'm getting in here. Yeah, but it's still easier than going Cartesian. Can I split that up? What do y'all think? Can I split that thing up?
Yes.
Yes. I love it. You know that. I can factor out the r. Although some of you don't mind doing iterated integrals. I'll avoid it if I can. So I'm going to do 0 to pi over 2 of the cosine theta plus sine theta. And multiply this answer to the integral from 0 to 2 of, I'm going to factor out the 4, right? I'll put the 4 right there. And r factored out with an r becomes r squared, right? Is that okay with the factor? Oh, good. That can confuse you. So it's really good you see that. I factored out r with r, making it r squared. There's that 4 that got factored out. I put it right there. I could have put the 4 there. That just becomes 4 times r cubed over 3 from 0 to 2. And 4 times 8 over 3 is 32/3. So now, what's these? What's the integral of cosine? Sine theta. The integral of sine theta? Negative cosine theta. We got to go from 0 to pi over 2. So sine of pi over 2 is 1, 0, minus 0, minus 1. Take this number and multiply it to the 32/3. What is that number there, though? Is that 2?
Mm-hmm.
That's a 2. 2 times 32/3? We just found the work done by the vector field to move a particle along the boundary curve. The whole closed path. Super job. I know somebody's still copying, so I'll wait. Stokes' theorem is kind of neat, but we do it at the end because this is the one theorem that connected line integral with surface integral. Line surface. Well, the last 2 problems are what we're going to do. We're going to be using the opposite side because they're going to say use Stokes to do that. So we're going to go back and do that, which is kind of neat. We end this whole course going back to do what we did in 16.2, which I like. I want to get to review that. Remember when we had to find line integrals? It was just f dot dr. And you go, what's that? Oh, so we'll just do this. Right there. The only thing is, r of t means parametrized curve. Isn't that funny? Look at all the work I was doing. We had all these things with a curl of f. And we had to parameterize the surface. I'm saying, bypass all that. We're just going to focus on a curve, a little c. There's going to be a big surface. Look for the curve, the boundary curve to the surface. Now, it might be bounded above. It's not always bounded below. It depends. It depends on the image we use. So, hey, I figure out from the practice problems, I'll do number 10, and I'll do number 9. But, oh, everyone done copying? I'm going to look. Busy? I'll wait. I'll wait. Go right ahead. Because there's a lot up there. You sure?
Yes.
hey, I'm gonna erase this attack the problem part because we're gonna attack it the other way. Alright. Use Stokes' theorem to evaluate curl of F dot ds. Alright. This out of the way. What's the vector field? They've got, by the way, they call this the flux of the curl that F across surface S. Use Stokes' theorem to evaluate the flux of the curl F for F vector field across surface S. Alright, so where F of x, y, z equals 2yzi plus x to the k. What's S? S is the part of the circular paraboloid. Z equal to x squared plus y squared. Below z equal to 4 with upward orientation. Again, can you help me make a picture? Use Stokes' theorem to evaluate this curl, I'll put an S there, curl of F dot ds, where F is 2yzi plus x cubed, and S is the part of the circular paraboloid z equal to x squared plus y squared below z equals 4 with upward orientation. Let's draw a picture, but our focus is just going to be the boundary curve, whatever it is. We'll draw the surface, but our focus will be right. A paraboloid just opens up like this, like a windsock. Okay. 4 notches, 1, 2, 3, 4. There goes the windsock. It's opening up, and it intersects z equal to 4 in a circle path. At z equals 4. So here's z equal to 4. They said with upward orientation. So upward orientation means normal vectors off this surface here like this, which means the path will be moving counterclockwise. So I just want as viewed from above. That's what I want you to think of. And when the path of that curve, think of a particle moving along that curve. Oh, by the way, do you agree that yellow curve is the boundary curve? See, sometimes it's below. If this thing was tipped upside down, you'd have a boundary curve down like in the xy plane. But this thing is opened up like this, that's the boundary curve. But I want to point out, you go, which way are we going to move? Because that's important to us when we do line integral. Am I moving that way or that way? We're going to be moving counterclockwise as viewed from above. And the reason is because they said upward orientation. For upward orientation, that means as long as, I'll say it again like the book said. Let me read it from the book. He goes, this means that if you walk in the positive direction around the curve, your head points in the direction of normal vector n. Your surface will always be to your left in that case. And sure enough, if I walked around like this, the surface is still to my left, isn't it? The surface is still to my left. Okay? Good. All right. So we got it, but what's so cool about this problem, how are we going to attack it? I want to just kind of separate all this here. This is how we attack the problem. Like that. Which is so interesting. Who cares about the surface now? I just want that curve. I just want the curve. So let me find it. I better take this off so we can get it right there. What is this curve? You gotta help me parameterize it. Can you help me parameterize that curve?
Yes.
R of x and y? No, it's just R of t, right? R of t. And we haven't done this in a while. Do you remember how to parameterize a circle. And I should get 3 components going. So I'm going to make sure I move this over. And I'm just going to say we're going to parameterize this curve. Right there. That one right there. R of t equals, I'll get my 3 components right. Want to use cosine sign? Because it's a circle. What's the radius though?
2.
Brilliant. You all know the radius is 2. Now how do they know this? They're setting this equal to that. They're looking at the equation of that circle. So I'm going to go off to the left here. They realize when this meets this, x squared plus y squared equals 4. That means the radius of this circle is 2. So to parameterize this circle, they're saying it's 2 cosine t for the x component, 2 sine t for the y component. What the heck is the z component? Man, you're good. I know that's tricky, just from experience. So I want to make sure everyone sees this. I'm not putting a 0 there. It's up, that curve is up in the air, it's equal to 4. Now this is the z-axis, the y-axis, and the x-axis, the positive z, positive y, positive x-axis. That curve is up, that's equal to 4. Now since this is Stokes' theorem, we're talking about 3-dimensional space here, right? So we're going to say that's a 4. Hey, I do want to point out, maybe one in the practice that I can't recall, but what if that curve was down in the xy plane? Guess what this number has to be then? 0, very good. Cool. But that's a 4, so we're going to leave it. Let's do the line integral. What's my limits then? See, isn't this bizarre, everyone? I only have a single integral here. It's been a while since we did that. 0 to 2 pi? All right, I'll put F here. Two yz here. What goes here? Y component. 0. And what's the z component?
X cubed.
X cubed. And then, all right, that's out. What goes here? What I have to do, F composed of RT dot R prime of T dt. And go from, 0 to 2 pi. That's what I'm going to do. So eventually, what am I going to substitute for this y and this z? That's going to go right there. This is going to go right there. What's going to go for the x cubed? That's going to get substituted there. And then we're going to dot what? R prime of t. So what is R prime? What's R prime of t? The tangential vector. Or we can just say tangent vector. What is it? Negative 2 sine t? 2 cos t, and what's the derivative of 4?
0.
Alright, I'll put that here. So just be careful when you do a line integral, this is always R prime of t. So I am now going to substitute all that in there. I wrote it like this, but I'm now going to substitute. What becomes the y, what becomes the z, and what becomes the x cubed, right? So I'll do it. Ready? What's 2 times this times this? What's 2 times this times this? Okay. Let's see, here I go now. 2 times 2 sine t times a 4, comma 0, comma, what's that last component? The last component is just x cubed, which would be 2 cosine of t all cubed. What is 2 times 2 times 4? 16. So I get 16 sine t. 0. 2 cosine t cubed. Dot this. the dot product? I get negative 32 sine squared 2. Do you all know how to do an integral of a sine squared? You need, very good, you all know you need a trig power, it's, yeah, they call it the power reducing identity. It's 1/2 minus 1/2 cosine of 2t. So I'm going to put that in here. I'll put the negative 32 out here though. 1/2 minus 1/2 cosine of 2t. That's the power reducing identity for sine squared. I just put the negative 32 out there. So what's the integral of 1/2? I get just 1/2 t, right? Okay. This becomes negative sine of 2t, but by a u sub, a 2 gets denominated with that 2, which becomes a 1/4. I do want to point out, I really didn't work out the math for the u sub. Is everyone okay that they can see that? Yeah, because you've done u sub so often that this, I actually let u equal to 2t. And then I got the 1/2, and I put the 1/2 at the 1/2, make another one. So that, I just want to make a note, this is by a u sub. This right here came out by a u sub. In case you want to work all that out. Did anybody need to see that u sub? You sure? I let u equal 2t. Yeah, I figured you all get that. And I'm just going to plug in what? 0 and 2 pi. Alright. What do we get for this answer? I get negative 32 times, I can put a big bracket. We'll do this minus this.